Welcome to This Explainer. Today, we're unpacking something you've probably eaten hundreds of times but likely never really thought about from a scientific perspective. We're going to unpack the hidden history, the microscopic biology, and the sheer thermodynamics behind engineering the absolute ultimate bowl of popcorn. Seriously, there is a lot more going on inside your microwave than you might think.
Okay, let's jump right into this by looking at this massive number, 135 psi. That's 135 pounds per square inch. This represents the explosive internal pressure that's literally building up inside a single tiny popcorn kernel just before it pops. To put that into perspective for you, that's roughly the pressure of a high-end racing bicycle tire, but trapped inside a shell the size of a pea. It's essentially a high-pressure time bomb made entirely of starch. Section 1. An ancient snack phenomenon. The 9,000-year history of Zea mays everta. Now, popcorn is definitely not a modern invention. Its roots actually trace all the way back to the very domestication of corn about 9,000 years ago in central Mexico. The specific strain we use, Zea mays everta, has literally been alongside human civilization for millennia. Just tracking its incredible journey, we have fossil evidence of popped corn from 4700 BCE on the coast of Peru. Thousands of years later, ancestral Puebloans were leaving popped cobs in New Mexico's Bat Cave around 3600 BCE. But, it wasn't until 1893, when Charles Creedors debuted his steam-powered popping machine at the Chicago World's Fair, that popcorn really became a commercial street food. And then, of course, in 1981, the first microwave popcorn patent completely revolutionized how we snack at home.
During the Great Depression, popcorn was one of the few treats people could still actually afford, at just 5 or 10 cents a bag. Then, during World War II, when sugar rations decimated the candy industry, Americans compensated by eating 3 times as much popcorn. This dirt-cheap production eventually cemented its absolute dominance in movie theaters. As this quote from film historian Stuart Hansen perfectly highlights, the markup on popcorn is absolutely staggering. Theater owners quickly realized they can make vastly more money selling high-volume popcorn than they ever could from the actual movie tickets.
Section 2. Anatomy of a kernel. The biology of a perfect pop.
So, not just any corn can pop. You can't just grab sweet corn off your dinner table and expect a cinematic snack. A perfect pop demands a very strict biological checklist. First off, you need the right flint corn variety. Second, it has to have a highly precise internal moisture level, right in that sweet spot between 14 and 15%. Too dry? It won't pop. Too wet? The shell softens and breaks way too early. Next up, you need an incredibly thick, tough outer hull, which we call the pericarp, measuring around 107 micrometers. And finally, the starch inside needs a high amylose content of over 23%, and it needs to be packed together super tightly.
You can really see this contrast when you look inside the kernel's endosperm. When we look at corn biology, there are 2 distinct regions in there. We want the tightly packed, hard, crystalline material known as the vitreous endosperm. This type has that high amylose we just talked about and creates massive expansion. On the flip side, the floury endosperm is soft, opaque, and full of empty void spaces. When a kernel has too much of that floury endosperm, the water vapor just leaks right into those empty spaces instead of building up pressure. The result? A very sad, disappointing, poor pop.
Looking at the micromorphology here, these scanning electron micrographs show us exactly what's happening on a microscopic level. Looking at the highly expanded kernels, notice how incredibly dense and compact those starch granules are, without any empty spaces at all. Now contrast that with the images of kernels that had a really low popping expansion. You can clearly see individualized starch granules surrounded by empty voids. Simply put, those voids are the ultimate enemy of a good pop. Depending on how that endosperm actually expands, we end up with 2 distinct shapes of popped corn, which the industry calls flakes. First, you have mushroom flakes, which are highly spherical and really sturdy. Because they don't break easily, they're excellent for commercial candy coatings like caramel corn. Then you have butterfly flakes, which have these irregular protruding wings. They're much more fragile, sure, but they offer a wonderfully tender mouthfeel. That makes them the absolute preferred choice for movie theaters.
Section 3. The physics of popping. Let's look at the thermodynamics inside a pot.
Right, so now that we've identified the perfect biological kernel, we need to apply some heat. This is exactly where biology hands the baton over to thermodynamics. When you drop a kernel into hot oil or hit start on your microwave, the temperature rapidly climbs. And when the inside of that kernel hits exactly 180 degrees Celsius, about 356 degrees Fahrenheit, the magic happens. The trapped internal moisture instantly turns to steam, but because that thick pericarp acts like a pressure cooker, the steam can't escape. Instead, it forcefully pushes into the hard starch, gelatinizing it into this cohesive, viscoelastic, jelly-like mass. And the pressure just keeps rising and rising until the pericarp violently ruptures.
Okay, let's dive into the core thermodynamic concept governing that crazy rupture: adiabatic expansion. Because the pericarp breaks so suddenly, the highly pressurized water vapor expands outward in literally a fraction of a second. It's moving so unbelievably fast that the hot steam doesn't actually have time to exchange heat and cool down against the surrounding room temperature air. This rapid expansion basically freezes that jelly-like starch into an airy foam almost instantly. This fascinating bit of physics is the exact reason why a freshly popped piece of popcorn is still piping hot the moment you touch it.
Remember that 135 psi figure we talked about at the beginning? Well, the yield pressure required to actually break that outer shell is roughly 200 times normal atmospheric pressure. To endure that kind of stress without breaking early, the tiny popcorn kernel has a yield strength comparable to solid polyethylene plastic at room temperature. No joke, it is an incredibly strong little seed.
Section 4. Hacking the perfect pop. Let's explore the vacuum chamber experiment.
Knowing the thermodynamic equations behind adiabatic expansion, physicists actually realized they could hack those limits to artificially engineer giant popcorn. In the commercial popcorn industry, success is judged by three major variables. First is sigma, which is the total expansion volume of the batch. Second is pi, the individual flake size. And third is omega, the percentage of unpopped kernels, which the industry affectionately calls old maids. The ultimate goal? Maximize sigma and pi while driving omega as close to zero as humanly possible.
So physicists theorized, if popcorn expansion stops when the internal pressure equalizes with the outside air, what would happen if we just removed the outside air? They designed an ingenious vacuum hack. They placed 20 grams of kernels in a modified sealed pressure cooker. They applied heat, and just as the kernels were about to pop, they flipped on a vacuum pump to suck the air right out of the pot. They ended up popping the kernels at a staggering 1/30th of normal atmospheric pressure. The results? Totally mind-blowing.
As we compare the normal pressure to the vacuum pump results, you can see the overall expansion volume of the batch literally doubled. Whether they used cooking oil or dry popped them on a mesh screen, dropping the pressure drastically multiplied the yield. Just to put that into perspective, 20 grams of kernels normally yields 1 8-ounce cup of popcorn, right? Under a vacuum, it yielded 2 full cups.
Now looking at pi, the individual flake size also nearly doubled. Because a flake is a three-dimensional object, doubling the volume doesn't necessarily mean it looks twice as wide to the naked eye. The radius only increases by a factor of about 1.2. But volumetrically, every single popped kernel contains significantly more of that airy, starchy foam. They are huge! Best of all, the amount of wasted, unpopped old maids, our omega variable, plummets by a factor of 5. Under normal pressure, you always have a bunch of those frustrating, tooth-cracking kernels sitting at the bottom of your bowl. But by lowering the resistance of the surrounding air, even kernels with slightly weaker internal pressures were suddenly able to successfully pop. It makes the entire process incredibly efficient and, for a manufacturer, highly profitable. So as we look at the physical limits of starch expansion, it really leaves us wondering. If physicists have proven that a simple vacuum pump can double popcorn volume and virtually eliminate unpopped kernels, when will the industry catch up? Are we just a few years away from commercial vacuum-sealed poppers arriving at our local movie theaters to give us the ultimate, scientifically perfect pop? Next time you hear that familiar popping sound in your kitchen, just remember the 9,000 years of history, the complex biology, and the intense thermodynamics happening in that tiny, explosive kernel. Thanks for joining me on this explainer, and keep questioning the science of your everyday world.